The outlook for 2012 is very good in the sense that we're expecting now that the machine will continue to operate very well, that will go to higher, possibly a bit higher energy, 8 TeV instead of 7, and take about 2 to 3 times as much data as we had in 2011. At that point, we'll have a very good, let's say, very, very good sensitivity for the Higgs particle. If it's low mass, we'll be able to definitively understand that. More importantly, I think, even then, well, as important, we'll have the ability to really start to look for supersymmetry in some of the areas that are still very, very possible, but very difficult to reach. And then, of course, we'll do many other measurements that are very, very crucial to understanding the standard model, to understanding whether there are other forces. We can extend our reach in mass to higher and higher masses. But the main program will be the Higgs, of course, and supersymmetry, and they're very interrelated. Going beyond that into the shutdown in 2013, 2014, we have a massive amount of work to do. There's a huge program of upgrades to the detector, also to the accelerator, of course. And then we hope to come back in 2014, maybe early 2015, at much higher energy, at nearer to the design energy of 14 TeV, and very high luminosity. And then, assuming we found something in 2012, we'll be able to study it in much greater detail, and the program will continue from there. The Higgs mechanism is really very simple in many respects. We have in the universe, everywhere, the potential for particles to exist. These are fields, vacuum fluctuations. The Higgs is among those. And if the temperature of the universe were very high, it would have really no effect, because its effect is very much randomized. But at a certain point, it froze. The Higgs became very well aligned throughout the universe in its internal dimensions. And when that happened, it coupled directly to other particles, giving them mass. It's very much like what the Stoics talked about more than 3,000 years ago. There's something that permeates the entire universe that gives all things substance. And this is exactly what the Higgs particle does, and the Higgs field does, once it's been frozen out in this way that I described. Now, the interesting thing is, unlike perhaps the image you have from the Stoics, that we are some sort of ghostly figures that the Higgs gives substance to, it's really at the particle level that the substance is obtained. And if there were no Higgs mechanism, we would just simply disintegrate. We would not be here. So the latest data are quite interesting. Up until this summer, it was clear that Higgs above a certain mass was ruled out, at least the standard model Higgs. Because in our standard model, we know as a function of mass how many Higgs should be produced. There are other models that are more difficult, in a sense, to produce the Higgs, so we wouldn't see them necessarily. But for the standard model, we ruled out quite a large range, and we left really only a very small 25 GeV range between 114 and around 140. In the newest data, we've probed this range now much more, with much greater sensitivity, and it's clear that we cannot yet say something definitive. But there are some tantalizing hints, okay? So 2012 will be the year, in some sense, for us to really understand that region. And if those hints are for real, we may have a strong observation. Of course, there's always the chance they go away. And if they go away, then we know the standard model Higgs is not the right Higgs, but it doesn't mean there's no Higgs. So we have to study and continue to look. It does, however, it will, and it does have significant implications if we don't see anything, for sure. If we find the Higgs at low mass, obviously we'll all be very ecstatic, okay? And it's very exciting in the sense that we've already ruled out, as I said, the range above about 140 times the proton mass. And what that means, in fact, even within the standard model framework, is that there has to be some other physics. We're not sure exactly where, but it already tells us some new physics has to exist. And the lower the Higgs mass is, in fact, the closer we know that new physics must be. So if we discover a Higgs at 120, 125, something like this, it doesn't guarantee we'll find new physics, but it means that there is something more out there. And of course, for us, that's always very exciting because we're explorers and we want to find new things. The Higgs particle, as I said, solves many problems, particularly the origin of mass. But the real problem then is that in calculating the Higgs mass itself, we don't get anything that makes any sense in some sense. It seems very improbable that it could be finite, and if it's infinite, then that makes no sense. When you introduce supersymmetry, this is a symmetry that is like another dimension in the universe. For all the particles that exist, it creates a mirror image of them. That's really very beautiful, very elegant. And it turns out that those additional particles cancel out all these bad effects that you'd have in calculating the Higgs mass. So it makes the Higgs mass perfectly natural and very sensible. And it is a very, very fundamental symmetry. And it's very, very beautiful in this sense. It has many other very interesting effects. It shows that all the forces will unify at some high energy, which is just amazing because this is what we like: unification, simplicity. It also explains why the Higgs mechanism occurs, which otherwise we wouldn't be able to explain, even though we know how to describe it. So supersymmetry is a very attractive and very beautiful theory. Dark matter is not really understood. We know it must exist from the way the galaxies move and from what we see and how light penetrates different regions of the universe. We know it's there and we know it's very abundant, but we don't know what it is. There's a very good chance, though, that it is a supersymmetric particle that's stable, very light, relatively light, I should say, and which doesn't interact very much. Since we think that dark matter, or we have very good evidence that dark matter is 5 times as abundant as normal matter, this means that it had to have been produced very copiously at some higher energy. And if that energy is comparable to something we can reach at the LHC, which we think it is, in fact, in the case of a supersymmetric dark matter particle, then we can access it and we can make these things. And so we are looking. Unfortunately, we haven't found it, but we have many, many searches that have searched in many areas. It's a bit like it's a bit more difficult than the Higgs, though, because there are many, many places you could look. And we have been pointed to new areas now by theorists that are very, very promising. So in 2012, those are the areas we'll be really, really combing very carefully for supersymmetry and for the dark matter candidates. So the Higgs particle creates a certain complication in when you try to calculate its mass. And there are several ways to solve that complication. And in all of those cases, you introduce something along the lines of new dimensions, either new fermionic dimensions, we call them, which are basically new sets of particles, or possibly new spatial dimensions. Space dimensions can have a big effect. And that would limit the impact of this problem we have on Higgs. So there are many people who think it's very interesting to look for additional dimensions. And one of the consequences of additional dimensions that are large, relatively large, would be that we could produce black holes at the LHC. These black holes are immediately they dissipate, they vaporize, but they leave behind a very interesting signature of lots of different particles in kind of equal measure, and unlike anything else we would see otherwise. So we're very seriously looking for those. Extra dimensions would also entail the creation of particles that would just escape the detector and leave behind no trace. So we'd see imbalances of energy. We're looking for those. They would tend to couple in many theories. They would these extra dimension particles tend to like to couple the photons. So we have many searches looking for photons plus missing energy. There are also the possibility of W prime and Z prime particles. These are essentially force carriers for a new force. And they'd be very heavy, considering that we haven't seen them up to now. And there are many models that find these attractive, because we already know that the existing force carriers, for instance, are all left-handed somehow. This is refers to their spin, if you like, and other properties. And there's an imbalance and kind of a missing dimension or the other side of the mirror, if you like, that's missing. And these could be just more massive. And this would actually help to solve many issues, including why the neutrinos have small masses and things like this. There are many, many interesting phenomena that one could look for that could explain many of the issues that we have right now in particle physics. So CMS is studying, in many areas, studying asymmetries of matter and antimatter. We've looked, for instance, at production of heavy quarks and their anti-partners, the top and the anti-top, for instance. So far we see very good balance there, but it's very early in the game. We're also studying B hadrons, they're called, and B hadrons are known to have an asymmetry that's very interesting. It's very slight, but it tends to give a slight increase in the number of matter particles over antimatter particles. Many people feel this could help us understand why the universe is mostly matter versus antimatter, but it's really too small to explain that, actually. And so we're looking to more significant new phenomena that could help unravel that question. Some of it could be in the form of particles that actually live in another dimension, perhaps even related to the antimatter that were produced and disappeared in the universe, but balance the whole equation out. So there are many searches that hopefully over time and with large amounts of data from the LHC, we'll be able to start seeing some of these, some hints of these types of particles. So in terms of looking for the smallest building blocks of nature, what we know is that the LHC can be thought of as a microscope. And in fact, the higher the energy you have, the smaller the size of things you can see. And the LHC is, in that sense, the most powerful microscope ever built by man, by a large amount. And every time we have a step up in energy, we'll be able to look smaller and smaller dimensions and try to probe the quarks inside the proton to see if there's any structure there. We've already done this for 7 TeV, and we don't see anything yet. But when we go to 8 TeV, we'll look again. When we go to 13 or 14, we'll continue to look. And although we don't expect to find anything, you know, one can never avoid looking, because it wasn't true that anyone had expected to find quarks once upon a time. So this is certainly part of our search strategy.